All right, we're going to look at the second part of section 2 here, which talks about the derivative as a rate of change. So far we used the derivative to find the slopes of tangent lines at different points. So if we consider this, if you remember slope we consider a rise over run from algebra, or the change in y, or the change in x. So that's for a line. So with our curves, we calculated dy dx. Well, this similarly says kind of the same thing. The dy is the change in y, and the dx is the change in x. The only difference is it's not necessarily on a line, it's on the line that's tangent to a curve at a certain point. But the concept that it's the change of one variable over the change of the other is kind of the basis of how we can use the derivative as a rate of change. So one thing we'll look at, just a kind of easy example, is we'll look at how something moves. So if I look at something how it moves, things can speed up, they can slow down, they can go at a constant speed. But a lot of times we'll give these in calculus and physics, we give these equations to denote their position. So in this case, if I have an object that moves along a linear path along a number line, such as position after time t is given by this function t squared. So I have this object, so we have this number line. So we have this object, we can make it a car. It's a terrible car, but you get the idea. So after 1 second, this car has gone 1 squared units. Now I don't know what this unit is, but we'll say it's gone 1 unit. So in 1 second, we'll say t is in seconds. It doesn't really matter, and we'll say this is in, I don't know, feet. So in 1 second, this has gone 1 foot. So it's not going very fast. So after 2 seconds, it's going 2 squared, or 4. So in 1 second, it only went 1 foot, but in the next second, it went additional 3 feet. So we went 1 for the first second, and then we went 3. And now the next one would be 3 squared, which is 9. So that's going to be somewhere out here. So in this case, we add 5. So we went up 1, we went up 3, we went up 5. The last one is going to be 4 squared, and it's not the last one, this thing will keep going, 16. So in that case, we'll add 7. So as you can see, every second this thing is going further than it did the previous second, so I think we can agree that this thing is not going at a constant speed. One thing I can say is that it is probably speeding up, because at every second it goes a little further than it did before. Now the real question is, what is the object's velocity? So how far is it going? So if you look at the speedometer in this car, what is it reading at every second? I think we can agree that it is not a constant speed, it'll change. So at some point you're accelerating and this velocity is increasing. And in theory, it's going to keep increasing forever and ever and ever if you consider it going with this function. So the idea is, how can we figure out what the speedometer reads in this vehicle? How does your car figure out how fast you're going at any given second? So the first thing we'll do is we'll look at the average velocity. So the average velocity in general is going to be how far you go versus how long it takes you to get there, just like general speed. So if we want to know the average velocity in the interval 2 to 4, so we're going from 2 to 4, then we'll figure out how far we went. So that's 16 minus 4, and we'll figure out how long it took us to get there, 4 minus 2. So that's going to be 12 divided by 2, which is going to be 6. And in the units we use, it's going to be feet per second. So if you think about what we really just did, this is essentially s of 4 minus s of 2 minus 4 divided by 4 over 2. So this is the average velocity in an interval. Now, if you think about this, this doesn't give us a real good idea of what's happening at a certain time. Maybe we want to know how fast this thing is going at 3. So you might think 3 is kind of in the middle of these. Maybe we're going 6 feet per second at 3 seconds, and maybe we are. We could do another one. We could say maybe we do something slightly smaller. Maybe we go from, instead of 2 to 4, maybe we go from 2.5 to 3.5. Now I'd have to figure out what those are, but if I think about the average velocity, it's going to be s of 3.5 minus s of 2.5 over 3.5 and 2.5. So what I'm trying to do is I'm trying to get this closer to 3. So again, it's this whole concept in calculus where we're trying to approach a value, but not actually figure out what's happening at that value. So this is going to be 3.5 squared minus 2.5 squared all over 1. So I'd have to figure out what that is. So if I do this, this one will also give me 6 feet per second. Now, it doesn't always have to do this. It could give you a different value. In this case, both the interval from 4 to 2 and from 3.5 to 2.5 both gave us 6. So you're kind of seeing maybe this is approaching 6. But again, it does not have to approach the same value. We just got kind of lucky in this case. So the question is this really what's happening at 3? Can we feel confident that's what's happening at 3? Well, we can feel somewhat confident, but I'm not sure it's 100% true until we look at the calculus. But in general, we could say as you get smaller intervals of t, of delta t, so this is basically the difference in time, we kind of assume that the average velocity should approach the actual velocity. So as you get really, really, really close, it should really approach our actual velocity. Sometimes we refer to this as instantaneous velocity or instantaneous rate of change. And the big concept is this. So as your velocity changes, as it gets, those intervals get smaller and smaller and smaller, your instantaneous velocity v actually can just be approximated by your derivative ds dt, because this is just going to be change in distance or position, because we called s position, over change in time. And your general speed formula is always distance equals rate times time, or rate equals distance over time. So the same idea. So as we take these smaller and smaller increments of delta t, the difference in those two, as that difference goes to 0, is just the derivative. So instantaneous, what's happening at that second, you can just calculate the first derivative of a position function. So if you look at this problem, we have a new position function. It says 2t squared plus 5. So we're going to find the average velocity over the interval 2 to 2.1, and then the instantaneous velocity at 2. So the average velocity is going to be s of 2.1 minus s of 2 over 2.1 minus 2. That makes the denominator 0.1, nothing crazy there. So the top I'll have to figure out, so that's 2 times 2.1 squared plus 5 minus 2 times 2 squared plus 5. And so we'll have to calculate that numerator. So if I calculate this, this gives me 13.82 minus 13 over 0.1, which should give me 8.2. And I don't really have a unit, so we'll say units per whatever time it is. So feet per second or miles per hour, whatever it might be. So is that what our speedometer says at 2? I bet it's pretty close, but if you want to know the instantaneous velocity, it's really simple now. Because we said the actual velocity, what you would see on your speedometer, well, except for the sign, because velocity could be negative, we'll just take the derivative. So s prime of t is just 4t. That's really easy because it's just a basic derivative using our rules. So the derivative at 2 is going to be 8. So 8 units per unit time. So in 2 to 2.1, which is a pretty small interval, we get 8.2, but the instantaneous velocity, what you see, is actually 8 units per unit time. So the big thing is your derivative is going to give you your instantaneous rate of change comparing two variables. So in this case, we did speed and velocity because that's a pretty easy thing to understand. But it's really can be defined by anything. So your average rate of change for any kind of object can just be given by subtracting the two y values over the difference in the two x values, or delta x. But your instantaneous rate of change, how things are changing in regards to one another at a given time, is given by the derivative. Now, the one thing you got to remember is this changes. So in this previous problem, at 2 seconds, it was going 8 units per second. But if I go to, say, s prime of 4 down the road, that's going to be 32 units per unit time. So it's speeding up. It's going faster. Its velocity is increasing. So at 2 seconds, you look down, your speedometer says 8. You look at 4 seconds, it says 32. So obviously this car is accelerating somehow because it's going from 8 to 32 in its velocity. So you can do this with other things as well. Here's a couple examples that I found. So anytime you're comparing two examples, if we want to know how one variable is changing in regards to the other, we can just look at the derivative. So here's an example where it says the sphere is being inflated to give larger and larger radii. Find the rate of change of the volume of the sphere if the volume of the sphere is given by 4/3 pi r cubed with respect to r. So we want to know how fast is the volume changing as the radius changes. So you can think of this sphere, or a balloon, or a ball of some sort that we're inflating. So the volume of this ball is 4/3 pi r cubed. So this is my radius. So if you think about it, if I'm increasing my radius when it's small, will it increase the volume as much as if I'm increasing that radius when the radius is larger? So if I take the derivative dv dr, so that's how the volume is changing it with respect to its radius, then this is, I'll bring the 3 down, so 4/3 times 3 is 4 pi r squared. So how the volume changes with how the radius changes is just given by this derivative. So if we think about this at r equals 1, dv dr would just be 4 pi. So the volume is increasing by 4 pi units when the radius increases at 1. So as your radius is increasing and your volume increases, when the radius is 1, it's increasing 4 pi. This would be cubic units per radii. You'll see though, if I do it at 3, if I plug in 3, r equals 3 for this, then I'll get 36 pi cubic units per radii. So it's a lot more. And think about this. If you increase a basketball or something by 1 unit, so the radius is 1, this is 1, say this is 1 inch. So if you increase it from 0 to 1, that's how fast the ball's inflating. Now, if the ball is bigger and you increase it by a whole radius, then the ball increases in all directions a lot more. So that volume has to increase a lot faster at that point for the certain radius. So as the radius gets bigger and bigger and bigger, the volume is increasing bigger as that radius changes. So again, we're always just trying to figure out how fast things are changing with respect to some other variable. So in this case, it's the volume with respect to the radius. Okay, let's look at one more. This is just kind of an odd problem I saw, but it's the same concept. The body mass of a bighorn sheep can be estimated by this function, where t is the days since May 25th. Find the average rate of change from 105 to 115, and additionally find the instantaneous rate of change at 105. So the average rate of change, you may remember this from pre-calc. Sometimes we use the abbreviation AROC. So there's AROC and IROC. IROC is instantaneous, AROC is average. So anywho, this is going to be m of 115 minus m of 105 over 115 minus 105. So my denominator will become 10. So m of 115 is going to be 48.775. And m of 105 is going to become 47.7 or 975. And again, this is just subtracting. This is just plugging these numbers in. I plugged in 115 to here, and I plugged in 105 to there, and got those two values. So then I'll subtract them, so I get 0.8 on the top and 10 on the bottom. So my average rate of change is going to be 0.08. And it's mass, I don't know, it's mass per day, because time is in days. I don't really know what the mass is, whatever units we're using for mass, pounds, grams, tons, whatever. Now my instantaneous rate of change, we'll see how that changes. So our instantaneous change, or if you want to call it the IROC, is going to be the derivative, which is going to be 0.3 minus 0.002t. And that's just taking the first derivative, taking the 2 down, the constant goes away. And so then we'll get 0.3 minus 0.002 times 105. And that's going to give me 0.09 mass per day. So at 105, it seems to be a little more, so this might be slowing down or speeding up, but that's the idea. So average rate of change, instantaneous rate of change, really just comes down to using that formula for average rate of change, or just finding the derivative.